The second topic we'll talk about with chapter 1 that couldn't be explained by classical physics is what's known as the photoelectric effect. And so the idea here is that if we have a piece of metal and we shine light on the metal, under the right conditions, electrons can be ejected from the metal. And so this was observed in the late 1800s, and there wasn't a good explanation as to why this happens. And so classically speaking, what we might think of, so light is an electromagnetic wave, and the electrons in the metal can interact with that light. And so we could have light coming in as a wave, it can push and pull the electrons, and if it does it with sufficient force, the electrons can come out of the metal and be ejected and become photoelectrons. And so this is classically the idea behind the photoelectric effect. So if that's the idea, if that picture is correct, what would we anticipate would be the properties that we'd expect? So we would expect that if the light is more intense, we should get more electrons. So the brighter the light, the larger the amplitude of our wave over here, and we should get more electrons, and they should also be going faster. And another prediction, classically speaking, if this is correct, is that the color doesn't matter, right? The frequency of the light doesn't matter, it's the intensity that matters. But what was experimentally observed was pretty much the opposite. So experimentally speaking, what happens is that there is, if we look at the frequency of light on, say, the x-axis here, and then our kinetic energy of the electrons on the y-axis here, what we see is, first of all, below a certain threshold frequency, we get no electrons. No matter how intense the light is in this region, right, where we're below a certain threshold frequency, there's no electrons. And it depends on the specific metal where exactly this threshold frequency is, but it exists for all metals. And then once we get to that threshold frequency and start emitting electrons, we get a linear increase depending on frequency, depending on the color of the light, we get an increase in the kinetic energy of the ejected electrons. So that increase depends on frequency. And so this doesn't, again, similar to the blackbody case, right? The observations don't match what we'd expect from the classical picture of what's going on with this. And so the intensity does affect the amount of electrons. So if you have more intense light, if there's more light present, you do get more electrons. So that part was correct. This part up here, but this part was wrong, and the fact that color doesn't matter is also wrong. And so what we need is a way to explain this, that there is this threshold frequency, why does this exist? And so the person who explained this idea of the photoelectric effect was Albert Einstein. And this was actually his Nobel Prize winning work. Even though he did so many other awesome things, and his name shows up all over the place in physics and physical chemistry even, this is the thing that explaining the theory behind this is what he won the Nobel Prize for. And so what Einstein did was he took Planck's idea of the quantum of energy, right? Specific amounts of energy that could be absorbed or emitted by a black body. And he said, well, let's apply that to light as well. So light comes in quanta. Quanta being the plural of quantum, which we call photons. So the energy of light also comes in a specific, specific chunks that we call photons. The energy is equal to that Planck constant, h, times the frequency. So that same equation that Planck had. And so by conservation of energy, the kinetic energy of an electron that's being emitted via this photoelectric effect is going to be equal to the photon energy, right? These little packets of energy that are coming in of light minus what's known as the work function of the metal, or this is the amount of energy required to remove an electron. So if you don't have enough energy in your photon, no matter how many photons you have, you're not going to be able to remove any electrons from the metal. This is a similar idea to, say, an ionization energy. It's slightly different because ionization energy is for gaseous atoms, whereas the work function is for a bulk piece of metal. And in most cases, they're different. It requires a little bit less energy to remove an electron from a bulk piece of metal. But the important idea here is this idea, right, that if we take conservation of energy, right, any energy that's coming into the system from our photons is conserved. We get the behavior that we plotted, right? This up here where we see an increase in kinetic energy as we increase the frequency of light. It's because as we increase the frequency of light, the amount of energy in each quantum, in each photon, increases. And so you get enough energy to kick the electron off, and the electron that gets kicked off takes the extra energy, excess energy, and is moving faster because if we're past that threshold of the work function. And so because we can't have negative kinetic energy, to get any emission of light, the energy of our photon has to be greater than that work function. And so this matches what we observe experimentally. And so again, we have the idea of a quantum applied to the energy of a blackbody emitter, and now it's being applied to light coming in and kicking electrons off of metal, right? This idea of the quantum, right, that we have discrete amounts of energy that are possible, shows up. So just a quick note on units when we're looking at these work functions and units. So phi is usually given, the work function, is given in units of electron volts typically. And so this is the amount of energy and electron gains when moving through a 1 volt potential. All right, and so 1 electron volt is equal to the charge of an electron, 1.602 times 10 to the negative 19 coulomb, times the voltage, 1 volt. And so the energy is 1.602 times 10 to the minus 19 joules. So if you need to make conversions between electron volts and joules, this is the conversion. And so the other thing that kind of led people to realize there's something to this quantum thing, it's not just some mathematical anomaly, is that we get similar values, essentially the same to within the experimental error, values for H, right? So it shows up in both Planck's explanation of blackbody radiation and in Einstein's explanation of the photoelectric effect. And so this Planck constant is some constant that fits in both cases.